Thank you everyone for coming. So today we will have Professor Ariel Cintron-Arias from Eastern Tennessee State University talk about developing workforce with mathematical modeling skills. Thank you.
Thank you. So I guess everybody can hear me, right? And I'm very honored to be here. I would like to start by telling you a little bit about first, I have the camera in one side of me, and then there is a second screen, second desk. So it's not like I'm ignoring sometimes, but you will see me kind of looking in two directions. So a little bit about where I work. I mean, my formal training is in applied mathematics. In fact, back when I was young, when I was a graduate student and postdoc, I learned methods for simulating and modeling infectious diseases. That was my formal training. And then since 2009, I have been at East Tennessee State University, ETSU, which is the map that we have here on the screen. So ETSU is housed in Johnson City, Tennessee. It's the very northeast part of the state. We're close to Western North Carolina on one side and Southwest Virginia on another end, and sort of close to a portion of Kentucky. That's the part of the state where we are. And so we are a public regional university. And a part of what I want to do over the next 20 minutes or so is to share with you some efforts that I have in my the curriculum that I teach while I'm injecting modeling skills and really data skills in classes like pre-calculus, calculus, and linear algebra. So I also have some ideas about having a minor in modeling. That's towards the end. And then I promise I'll come back to this geography. So about 4 years ago, I became an ISTE certified educator. ISTE is the International Society for Technology in Education, and they're, as an entity, are very strong in promoting standards. And so what you're seeing there is a diagram with the subdomains of how the standards are divided. When you become a certified educator, you kind of need to do all of these areas. But for me, computational thinking was something that truly resonated with the things that I do with my practice. And so I want to say a few things here about computational thinking in terms of how ISTE phrases these things. Basically, computational thinking, there are like four different portions to it. There's something about formulating problems, something about abstraction. The models are these descriptions of these phenomena or these underlying phenomena describing some of these problems. There's something about data. Data is a very essential part of all this subdomain of computational thinking, collecting data, representing data, analyzing data, all towards geared towards decision making. This portion about decomposing problems, breaking kind of complex problems into smaller segments and working those smaller segments to extract meaningful key information to then basically extrapolate and find solutions. All these things. And then, of course, there's algorithmic thinking that has to do with like this sequence of steps, and finding solutions. And all these things are basically things that we as mathematicians are very well trained on, especially when we graduate as grad students, masters or PhDs or postdocs and walk away. A lot of these things resonate very well with us. And for me, I figured what they're talking about here, they call it computational thinking, but they're really talking about modeling. So, so what is my slides here? So let me switch and go back to full screen again. So what I want to share with you is how I align or do a little bit of modeling in various courses. At ETSU, we have a sequence for pre-calculus 1, pre-calculus 2. In pre-calculus 1, we cover mostly functions, linear functions, polynomial functions, exponential and logarithmic functions. And so the students work there, these projects involving modeling, involving data, in a way in which every student was assigned, these were COVID-19 data sets for the United States, and every student was assigned to a specific state And even though everybody was using a different data set, the set of questions or of guiding or exploratory questions was the same set of questions. So they were trying to address this in the same way, but this was not an exercise that had unique answers, and definitely was not an exercise with answers in the back of a book. This was very open. And so in this context with exponential trends, they also had the ability to use a log transformation and use the log transform data to a linear regression, estimate some parameters, and then transform that data into the original scale to then have some predictions of forecasting. And so they could assess if the complete data set was well suited for some type of functional form. If that was not exactly the best, then they could divide the data set into subsets or sub-intervals or subdomains, and then come up with their own assessment as to which one of these is better in their what subdomain. The other thing they were able to, once they had estimates for the constants, for the parameters, they were able to calculate doubling time, and they were able to basically compare this is where cumulative cases of COVID-19, they were able to compare how the epidemic was taking place, based on their estimates of doubling time. So these were some things that were um, meant to be very real life, very relatable. Okay, so that was pre-calculus 1. Pre-calculus 2, which is dedicated more to trigonometry, um, sinusoidal functions, they were using other data sets that are called influenza-like illness. So this is basically data for that has seasonal patterns. We get the cold, the common cold, the flu, usually during winter months, and then usually during the summer, those respiratory infections are less common. And so students would use those seasonal data sets to then explore various sinusoidal forms. So these are pre-calculus students, and the outcomes that they would produce, the things that would ask them to produce and that I would collect, were in three forms. They would write a report like a paper. This is very much the same type of laboratory report they would produce for biology or a chemistry lab.
I'll just follow you. Radishes, please.
Excuse me. So they could also produce an infographic, which was another form of reporting what they obtain. And the infographic was more in the spirit of a scientific poster, but maybe in 2 or 3 pages. And the other form is Microsoft has something called Microsoft Sway, which is like a mixture between a PowerPoint presentation and a website. So they produce all these 3 outputs. And of course, that also meant on my end that there was a lot of onboarding, and it was completely a process. It wasn't something you just say a deadline, collect one day, and I needed to give them some feedback in their drafts, draft version 1, version 2, and final version, and so on. So one thing that we do in calculus, this would be differential calculus, is that I use data sets where students do not have to process the data. So in the previous, what I was showing you, what the pre-calculus students do, part of what's involved is that they download a data set and they have to do some processing or curation using something like Google Sheets or Microsoft Excel. So in calculus, they use that every student is assigned to a country, to a data set corresponding to a country. These are COVID-19 data sets. These are daily new cases, but the data is already in a display that is interactive. So you're seeing there an animation where as you move the cursor over each data point, then you get a display of the value on the horizontal axis and the value on the vertical axis. So with this type of data set, then students would do an exploration addressing basically concepts they learn of applications of derivatives. They would apply about local extrema. They are going to apply their concepts, definitions about increasing curves, increasing and decreasing functions, and also they're going to address concavity. Now, when we learn calculus and learn all these things about applications of derivative, first derivative test, second derivative test, we are learning this in the context of a function that has a single variable. And that function has a very specific formula. We learn how to take derivatives and so on. What the students are doing here is that they are applying those concepts. So there is no formula. They only have a data set. There's a curve by connecting the data points, and they have to come up with some of these answers without this explicit formula. So these are some of the responses that they produce, as probably you can see here on the screen. I know this is very, very fast, but yeah, they're addressing about where a local minimum, local maximum, an interval they report where one of those things take place, and an estimate value where the actual extremum may take place. They're reporting intervals where the curve is increasing, where the curve is decreasing, and they're also reporting intervals for concavity, and with that interval where the concavity changes, and their best estimate or best estimated guess as to where there may be an inflection point. There, one thing that you may be able to notice in what this person wrote here is I asked them, I have part of the rubric I use is something that has technology attribution, specifically if they're using generative AI, they're expected to disclose what kind of technology and what type of generative AI they're using and how they're using it. So there needs to be a very clear statement of whatever they submit, who produced that, what was produced by the human, and what was produced by a computer. And then the third experience I wanted to share with you is something that I work with my linear algebra students. This is basically in the context of image compression or rank 1 approximations. But here, so here the data is also another scenario where every student is using their own data. Here the data is image data. And part of what, believe it or not, part of what makes this perhaps an impactful experience is that every student selects the image they're using. This may be an image from a pet, it may be an image from a landscape, from a plant, a species of flower, or something of that sort. And then they use that specific image to explore it and do the lower rank approximation. This also takes stages. I say that maybe 4 different stages. They start on the project, they use templates that I provide for them as Jupyter notebooks. And while we have class meetings, I have some of my students attending class via Zoom. Some of them may be with me in some location in person. And so during these class meetings, as they're making some progress, then what you're seeing here on the left, for example, is somebody sharing the screen. This is my own handwriting there where I'm annotating. This is another shared screen that was shared. Somebody getting a traceback error. This is very important, getting errors and brainstorming together about what's going on here, how to address it. So they are getting formative feedback during live sessions. There are also some discussions in the learning management system that are not for grade, are more to share or compare notes. So in between the scheduled meetings, they may be sharing, part of their progress. And then once they move on to produce the finalized version, then this is kind of what their final submission looks like. In this particular case, this was collected as a Microsoft Sway presentation also. So they were reporting the original image, the various approximations to that image, sometimes portions of Python code, that was the tool they were using, and some type-in text. This is one report from one student. This is another report where the student decided to, in addition to code and images, she was using the photo that she took of a flower. I think there may be a bee or something in that flower. In addition to that, she was also adding some handwriting, some of the underlying linear algebra that's part of the theory here. And she also had some portions of her Sway presentation that had type-in text. So it was kind of a combination. And yeah, so those are kind of like the the three scenarios that I want to share with you as far as some of the alignment that I do with my practice in classes like for pre-calculus, for calculus, and linear algebra. And here are some ideas about putting together a minor, perhaps in mathematical modeling. This can really have many names. It could be a minor in data science, applied data science, or modeling in general. More or less, there would be a minor, at least in East Tennessee State University, is something that requires between 20 credit hours and 25, more or less, between 20 and 25 credits. So there could be two camps here, courses that are required and then courses that will be recommended electives or guided electives. In the requirements, you'd have some foundation of calculus, some foundation linear algebra, and some introductory statistics. The calculus, it would suffice in some cases to just have differential calculus, just a sequence of one. But in some cases, you may have two calculus courses or maybe even three. Now, the other subdomain of courses, this is where the substance of modeling there will be at least maybe 3 or 4 of these courses on this branch. Something I call data wrangling or data manipulation. That, in my own experience, in our catalog, we have a course that's called mathematical computing, and I am promoting and we're working on switching that. This was meant for our math majors to get exposed into the basics of coding and programming in languages back in the day, like Maple, MATLAB, Python, and more recently R. Now I think what I'm trying to do is to make that math computing or computing for math majors to be more about data wrangling or data manipulation, and you couldn't do those tasks without learning the basics of programming. And so it's about learning how to write code, how to execute code, but all with a twist about manipulating mostly tabular data. And then there are courses, for example, 5 years ago, I was in the joint meetings. I had the honor of attending a workshop of CME-ODE, which now has evolved into a book, Differential Equations with Modeling. I do not know how people would teach DVQ without modeling, but I mean, that's another, we could be here talking about just that for hours. The typical numerical analysis class, I think today probably needs to be more about numerical methods for data science. Numerical linear algebra, here's another version of that. Computational linear algebra, definitely aligned with a lot of applications for neural networks, machine learning, even large language models, things of that sort. Time series course, operations research, that could be a numerical optimization class or some mixture there in the numerical methods. It could have a little bit of optimization methods, and definitely the various versions of modeling. There could be one here that mathematical modeling, that would make 4. Mathematical modeling, predictive modeling, stochastic modeling, statistical modeling. Of course, some of these things really are a function of the university and the specific department and the personnel, the staffing that is available to teach. Some faculty members would be, this is directly aligned, this is my research area, I feel very, very comfortable. Other faculty members would be like, this will be relatively new, I'm willing to step outside of my comfort zone this much, so I'm willing to like make another version of this class and maybe I can incorporate it. So it really depends. There could be a collaboration. Maybe not all courses have to be housed in one department. It could still be a minor in data or data science or modeling or applied modeling. It could be with courses from maybe more than just one department. That would make it actually very, very interesting. So I said that I was going to come back to the geography, and it's because in the process of arguing about how to inject skills in undergraduate curriculum that are geared towards modeling or towards data literacy, there is an actual movement right now to promote data science courses at the high school level. Now, this map here is a color code addressing data science education in K-12 in the United States. There are 4 different colors. It says K-12, but really this is mostly 9, 10, 11, perhaps even just 11 and 12th grade. So the states that are coded, that are represented in gray, grade would be tier 0. That is just a simple stage of research and development. The next tier, tier 1 and 2 are, excuse me, those are blue represents that a course in the state catalog exists, a course in data science. A data science course was created for the state catalog at the high school level. And the peach or pink represents that that course is currently under some kind of pilot version in various parts of the states. And there is currently professional development for educators taking place to implement such course. And then what's represented in red is a much more advanced stage where this course is actively being offered across several high schools in the state, and there is a lot more involvement. But this is kind of the state of data science. It is K-12 because even though this is addressing a high school course, for states where this exists, this type of activity exists, there are implications, alignments that happen in middle school and elementary school as far as promoting data literacy skills and even coding skills, because it's like a pipeline. These are states where they know when those students reach grade 9, 10, then they will likely have this as a pathway, this data science as a pathway. So I'm just mentioning this, which was last updated in 2024 by an organization called Data Science for Everyone. I'm mentioning this because when we are, as educators, in the process of creating curriculum, updating curriculum, perhaps creating a minor in modeling, these are the individuals that come out of this map. Those will be the individuals populating any of our efforts, So, yeah, I guess I'm very optimistic. So, and I think I don't know how we're doing with time, but I really want to. You may have questions, but I think we have a little bit of time. I wanted to do a demo. Okay, I was showing you some of the things that I do, especially with the pre-calculus and calculus students. And one thing that I probably did too fast, what I do with the pre-calculus students, where for us, pre-calculus is a very introductory class. There is it's kind of the point of departure. So there is no expectation they would have coding skills. Even Microsoft Excel skills are very tender. So the Desmos graphing calculator is one of the things that I use, and I just want to do a quick demo just to give you an idea. So here's a CSV file. I already have these 2 columns. I select the 2 columns, copy, and then I paste those data points into the Desmos graphing calculator. That's a scatter plot. Everything looks good. And then I want to show you why is one of the reasons why I adopt and love Desmos. So there's one column called X1, the first column. The second column is called Y1. So I type here Y1 equal. Instead of saying equals, I use the tilde, which is like approximate. And then here I would say something like cosine of X1. So, but to make this more interesting, I can have a coefficient here in front of cosine, and then maybe have another coefficient over there. I don't know. There's various versions of this. So there are 2 parameters, A and D. Automatically, the Desmos graphing calculator is doing a nonlinear regression. The user doesn't really need to know, everything let's add another parameter here, B, and then maybe another one here, another shift. This looks a lot better. So 4 parameters, Desmos is automatically doing a nonlinear regression, coming back with estimates. This is what I use with the pre-calculus students. Many of those students are working with me via Zoom with synchronous delivery. Many of those students are asynchronous students. So it's not even like I have ways of interacting with them, how I'm interacting with all y'all right now. So this tends to be a really useful tool. And so the other tool that is new to me that probably you know is called CodeUp. You go to CodeUp, you launch a new document. One thing you're not seeing is I already have a CSV file in my desktop, which I'm dragging here. And that's the CSV file I was using to copy and paste into the Desmos graphing calculator. So it was a very easy drag and drop. Okay. Yeah. Mm-hmm. Thank you, Yaping. So of course, there's all the columns of that thing there. So now that I have this here, I can choose graph. It immediately produces a graph over there, and then I can choose the columns that I want in specific. So for example, this column called time step, I'm gonna drag it into the horizontal axis, and then I'm gonna take this column called ELI, total, I'm gonna drag it into the vertical axis, and it produces a scatter plot. This is how accessible CodeUp is. So I'm now in the process of kind of redoing what I was doing with the Desmos graphing calculator in pre-calculus and maybe even calculus. I'm trying to reformulate some of those projects or labs using this tool, which is, I think, very, very promising and very accessible. So, yeah, okay.
Thank you.